So let me start. I'm actually very excited to do this because it's one of the few opportunities that we present a plugin that's developed by one of our co-vendors, and it was actually great. Let's see, my PowerPoint. Yeah, my PowerPoint is also starting. It was actually great to work together with the guys from ARK CLS to present this, to prepare this webinar, and I want to thank them, Tony, Tao, and Adrian again for working with me on that. Also want to thank Arnold Hoek for his help preparing this webinar. He was especially helpful for me to prepare the live demo. We will see later in the webinar. And then a final acknowledgement. What we present here is not only the work of DCB and ARK CLS, but is actually based on much of the conceptual work of Patrick Conley of BP. He developed this workflow to extract net pay thickness maps from seismic data. It was first presented at the EUG annual conference in 2005. But for people who want to learn more about it, I would actually recommend reading the 2007 companion papers in the Leading Edge about this workflow. Very well description of both the workflow and the uncertainty analysis that is attached to it. So today the webinar will be split in approximately two halves of the same length. First, I want to go over the concepts of the theory, and then I will do a live demo of the plugin. So that will be more or less on how to. A short recap of everything what we did discuss today, and then there's ample time for a question and answer session. Now the workflow is straightforward, but there are some whistles and bells to it that might get you distracted. So I want to encourage everybody, if you need more clarifications during the webinar, just to stay on course, ask the panelists for more information to answer your question. That's what they're there for. So let's start with the concepts. First, why would you want something like a net pay map at all? Well, first of all, it is a key property to know for reservoir appraisal. How economic is the reservoir? How much oil can I expect in a reservoir? Of course, that also depends on the porosity and the recovery factors, etc. But this is an important part of that equation. And then if a reservoir is deemed economical to develop, the net pay map is an important guide in how to develop a reservoir, where to put your wells and in which order to put your wells to develop a reservoir for maximal recovery. Of course, net pay can be based on contouring of the wells. That is the old-fashioned method where you extract the net pay from your wells at as many points in your field as possible, and then start contouring based on the well constraints and the geological insight you have. But of course, in many situations these days, like deep water and appraisal phase field development, we don't have that many wells, so that's a very hard exercise. And even if we have many wells, why leave all that lateral dense information that we have in our seismic data unused? So there are already methods to do this. One of the first publications, or maybe the first publication of this, is done by Brown et al. In 1984, and he bases himself on reflectivity data rather than impedance data as we do today. And the algorithm we're explaining today is moving from interface properties to layer properties. We were basing our estimates on a relative impedance volume, and at least one modeling study shows that gives improved results above working with seismic reflectivity. Well, before starting to explain the actual algorithm, I want to introduce two key properties that we will use today. The first key property is seismic net to gross, which is defined as seismic net divided by apparent thickness. The seismic net is the travel time through the reservoir or the pay And the apparent thickness is time thickness from the top reservoir horizon to the bottom reservoir horizon. Note that we say here an apparent thickness because this thickness might be different from true thickness. For thick reservoirs, the apparent thickness and the true reservoir thickness will be approximately equal. However, for thin reservoirs, due to tuning effects, the apparent thickness will be larger than the true thickness of the reservoir. And this is an effect that we need to correct for in our Seismic Net Pay algorithm. The other key property that I want to introduce you to is the average relative impedance of the reservoir. Here we take the top reservoir horizon, the bottom reservoir horizon. We extract and sum all the relative impedance samples in this interval and then average them. The key assumption, or what we're going to prove during this webinar, is that if you know the average relative impedance of the reservoir at a certain point, then you can say something about the seismic net to gross. And if you know the seismic net to gross, you can, of course, very easily multiply out that apparent thickness and arrive at the seismic net in two-way time. But you also can extend it over and one step further and actually arrive at the seismic net that is in depth. And that is what we will do today. Before we start with the data processing, let's discuss what data goes into this workflow. First, let's go in the OpendTect route. You can do everything you need here to prepare for the input for Seismic Net Pay in OpendTect. Typically, you can start with full or partial stacked seismic volumes. You would input these in the seismic colored inversion plugin to arrive at a relative impedance, and that will be your input to Seismic Net Pay. If you want to be a little bit more advanced, you can actually create a tune stack that is optimized to see either lithology or fluid saturation, and input that in seismic colored inversion and input that in your Seismic Net Pay. Of course, there is no need to do all this in OpendTect. If you have a relative impedance volume available from other sources, you can just import it in OpendTect and feed that directly to the Seismic Net Pay module. So a little bit about those preparational processes. First, about the seismic colored inversion. What we note is that the earth impedance spectrum, and note I say here the impedance spectrum, not the reflectivity spectrum, is red. You can very easily verify that by yourself by taking impedance trace from your wells and calculating a frequency spectrum on it. It's derived theoretically by Friso Brouwer in 1981, and it's confirmed through an empirical analysis of well logs by Waller and Hoskin in 1985, and there are a number of other publications too about the subject. By the way, I want to mention, no need to pen down these references. We will include them in a follow-up email that we will send to you after the webinar. So if you want to do more reading, you will have the references available. So the earth impedance spectrum is red. Why it's red, that's a nice aside. It's a little bit beyond the webinar, but I just wanted to tell you, if you look at a layer in the earth from some distance, you see multiple layers. Say you zoom in on one layer and you focus on that, then you will see in that layer patterns that are very similar to the pattern you saw when you looked from a certain distance. And if you take then again a new zoom and you look at there, you will see again very similar patterns. So that's kind of a fractal behavior. You cannot really descend the scale where you're looking at from just the layering. And that fractal behavior gives rise to power laws, etc., etc. And that gives rise to the red behavior for an impedance spectrum, and actually in blue behavior where you bias to the high frequencies for your reflectivity spectrum. So that is the philosophy behind that. Of course, during the seismic experiment, you register only part of the Earth impedance spectrum because you have a limited bandwidth in your seismic experiment. So you will missing some low frequencies, and you will have a high frequency cutoff. So your practical impedance trace that you can derive from your seismic alone will actually be a relative impedance trace. It's missing the low frequency trends, and it will have resolutions issues on the high end. So how to arrive at a volume with this relative impedance? That is done in the seismic colored inversion plugin on OpendTect. The philosophy on a very high level of that is very simple. Within an appropriate interval, you're going to look at the spectrum of your seismic data, the frequency spectrum. You also, within the same bandwidth, you're going to look at the spectrum of the impedances as you derive it from your wells, and then you create an inversion operator that transforms your seismic spectrum or your seismic data to data that has the same spectrum as the impedance traces in your wells. There's also a phase shift done, and that assumes that the seismic data is zero phase, but that's the only hard requirement that you have. The big advantage of this workflow is that you don't have to have a very exact wild eye, and that you don't have to derive seismic wavelets to do the inversion. So that is the one step, the seismic colored inversion step, that you can do in advance of the Seismic Net Pay calculation. If you want to be really tuned in either lithology or fluids in this Seismic Net Pay, because you of course can predict net sand or you can predict net saturation, you can focus on the tuned stack. Most of the theory is actually very well described in an article by Whitcomb et al. In 2002 Geophysics, 2002 Geophysics. So I will really browse high level through the philosophy. It starts with a gradient impedance. So you have a gradient volume that is a standard AVO output attribute, and an intercept impedance or an acoustic impedance. Typically, this analysis is done based on well data and on petrophysics, but then you take the logarithms of your gradient impedance and your acoustic impedance or intercept impedance, and you cross-plot your points there. And you overlay as a color attribute either saturation values or lithology values. This is of course imaginary, but here in the yellows I have put some sand points, and in the browns I have put some shale points based on a gamma ray cutoff. And you see that there's some separation, but because this scatter cloud is oriented diagonal in this crossplot, it's very hard to either define an acoustic impedance or a gradient impedance range that would separate the sands from the shales. So in very simple terms, what you will do is you will apply a coordinate transformation, actually in rotation, with an optimal axis defined by a chi angle that maximizes the separation, in this case between the sands and the shales. And you can also find the other chi angle that would maximize the separation to like hydrocarbon saturated plastics and non-hydrocarbon saturated plastics. So there you can optimize with different angles for different glow properties depending on what you want to see. You can apply the same chi angle on your intercept in your gradient volumes and create a tune stack, and then apply the colored inversion algorithm to the tune stack to either arrive at a lithology impedance or fluid impedance and see one of those preferentially. So that's about the seismic data and the resulting impedance volumes that are the input. The other imported input is the horizons. What you need to do is pretty accurately isolate the reservoir. And you will do that by taking the zero crossings above and below the reservoir. In our case, the reservoir is low impedance, highlighted by these yellow values. So you would have to find a horizon that has here a minus to plus zero crossing, and here plus to minus zero crossing. In OpendTect, you can either track them from scratch, or you can, if what's typically the case, if you already have seismic horizons available, resnap your horizons on your colored impedance volume. And that's what we did here. One thing I want to emphasize, it's not necessary that if you have a low impedance volume reservoir, that there are no high impedance events within the reservoir interval. It's perfectly okay to have high impedance events. However, in this case, the average impedance within the reservoir interval should be lower than zero to do a valid analysis. Also, these horizons, either through the isopachs, the apparent thickness isopach, and through gross thickness conversion of this isopach, are used at multiple points in the algorithm. So a proper picking of this top reservoir horizon and this bottom reservoir horizon on your colored impedance volume is critical to the success of this workflow. So let's go to the algorithm itself. Step 1, tuning and detuning. So far it sounds very nice that the average impedance relates to the amount of reservoir that you have in your reservoir interval. Sounds very logical. Unfortunately, the seismic experiment acts as a bandpass filter, and that causes tuning effects that need to be compensated for. So the first step in the algorithm is actually investigating what kind of tuning effects you have and creating a detuning curve. After you make the detuning curve, you have an equation that says the average relative impedance in your reservoir times a detuning factor that is specific for your apparent gross thickness at that point times a scaling factor would approximate your seismic net to gross. Well, how to create that detuning factor curve? We take a standard impedance wedge. Again, not a reflectivity wedge, but an impedance wedge. We convolve that with a bandpass filter representing the frequencies that are actually available in your colored inversion volume, colored impedance volume. So here we have the corner frequencies for a typical experiment, 4, 10, 75, 85. It's pretty critical to get these cutoffs right, especially the lower cutoffs are very important, as the algorithm is sensitive to them. In the thicker reservoir range, the tuning curve will be incorrect if you got these corner frequencies incorrect. The nice thing is that you partly can compensate for errors in your low frequency range by well calibration, so the algorithm is even robust to some extent for errors in that, but that is a very important parameter. Quickly going over this tuning curve, we see two things. This is again the result we see in color, the relative impedance with the dark values representing the reservoir. If we're in the thick end of the reservoir, we actually see that the amount of impedance that we measure stays approximately constant. That is because we're missing the very low frequencies that would be necessary to characterize the reservoir over the full range, leading that we have larger and larger apparent thickness and an approximately constant amount of average relative impedance in there, leading to a decreasing amount of the average. On the high end, we see that the relative impedance that is contained in the reservoir decreases because the actual wedge becomes smaller and smaller. However, at that end, we have tuning effects, and we see that the seismic horizons picked on the zero crossings are actually moving away from the actual wedge. and even from constant thickness for the very thin reservoir. So you will divide a smaller amount of relative impedance captured in the wedge by a constant apparent thickness, and with that we will again lose average relative impedance in that range. So that leads to the following tuning curve that you see here. On the lower axis you see the apparent thickness of the reservoir. On this axis you see a normalized response, impedance response. You see that for the very thin reservoir, you see that the average amplitude falls away quite quickly, and then if you go into thicker reservoir, you have a more slower fall away from of your average relative impedance. So you need to correct for that, and you create a correction curve. This is the detuning curve. You see that the detuning curve varies per apparent thickness. And for each apparent thickness, if you take the value of the detuning curve and you multiply it with the relative impedance, average impedance extracted from this homogeneous wedge, you should arrive at 1. So that is actually how the detuning curve value is calculated. Then there is also a scaling factor in there. I will talk about that in a moment. First I want to investigate if I have now a set reservoir interval apparent thickness. Is it really true that within that, for that apparent thickness, my net to gross is proportional to the relative, to the scaled relative impedance, average relative impedance in that reservoir. So we have done a number of modeling experiments here. For each experiment, we see the seismic net to gross that we know from our model exactly on the vertical axis, and we see the average relative impedance in the reservoir on our horizontal axis. These models are randomized, so the shields and the sands are recombined in random ways, random layering ways, however in a geological realistic way. So there's not a set layer configuration here, and that's important because what we see is that we see some scatter, and that scatter is related to the variations in internal layering within the reservoir interval. That internal layering is of course way beyond seismic resolution, below seismic resolution, but it will affect the outcome. And we see that we have approximately a linear proportional trend. So the high, or in this case the very low average relative impedances correspond with very high net to gross, and then it takes goes linear to about 0 net to gross for 0 average relative impedance in the reservoir interval. We see if our apparent thickness increases, that scatter plot becomes wider around the linear trend, and if it increases further, it becomes even wider. And those are two important observations. Thicker reservoir leads to more uncertainty, and net to gross values that are around 0.5 are leading to more uncertainty. It's kind of a scatter plot. You see it very well actually in this plot, that around 0.5 you see the highest departure of from this line, and we will discuss later why that is. Then finally, another very important step, that is the scaling. The scaling is derived from a scatter plot where at every point of your horizon you take the apparent thickness and you take the average relative impedance value, and you overlay the tuning curve, and you can move the tuning curve with the scaling factor a little bit up or a little bit down. If you just put it over the envelope of the scatter plot, you basically assume that the highest relative impedances at every apparent thickness are coinciding with the net to gross of 1. That might be a flawed assumption based on your geology. Some geologists like fans or nice beach deposits will have a net to gross of 1, but other geologies, sedimentary features, will never reach that value. Also, thicker reservoir is more unlikely to reach this value. And of course, you have a problem with the scaling if your reservoir apparent thickness range is only covering in part this tuning curve. So this is a step that has some pitfalls. And during the live demo, I will demonstrate a little bit more about this. So we're now halfway. I have a seismic net to gross in time. However, I would like to have net values because that is really what counts, and I would like to see them in depth because then I can compare them with wells. We do that in two steps. First, we go to a net to gross value in depth, a seismic net to gross in depth, and we'll see that what we need for that is only a velocity ratio between your pay, your reservoir sands, and your non-pay, your shales. And then we convert to depth in a two-step procedure. Convert to gross reservoir thickness using a preferred method that can be done in OpendTect, that can be done outside OpendTect, and then you just multiply out the net to gross value times the apparent thickness of the reservoir in depth, and you get a net depth estimate. First, I will derive an equation for converting seismic net to gross in time to seismic net to gross in depth. I won't go in all details of this derivation, but basically we convert our travel time through the pay formations into the equivalent thickness, and we do the same for the complete reservoir. Dividing these two quantities, we arrive at the equation where we see that the conversion from seismic net to gross in time to seismic net to gross in depth is only dependent on the velocity ratio between the pay of the reservoir formations and the non-pay or non-reservoir formations. This ratio is easily derived, for example, by cross-plotting in OpendTect a sonic log against a gamma ray log. Then we will calculate either in OpendTect or outside OpendTect a gross thickness map for the reservoir, and then multiplying this estimate for the seismic net to gross in depth with the gross thickness map, we arrive at the net thickness for the reservoir. So having done that, I have now some net depth estimates, and I can compare that with the values that my petrophysicist actually gave me in the wells. That is a step you have to be fairly careful with. First of all, we saw that there is inherent scatter in the relationship, that is inherent nonlinear and randomized behavior. Second of all, the definition of your petrophysicist about what the pay might be different than what the seismic data sees as good sense. And then third of all, especially if you have features that laterally vary very rapidly, well placement or the accuracy of the well placement becomes very important, and some uncertainty in terms of one or two seismic bins might lead to important departures in actually the seismic net pay or the seismic net that you derive at those locations. But as in this scatter plot you consistently underestimate your well pay with your seismic net pay, then you might go in and redo that scaling factor just to get that relationship a bit better and those wells fitting in a bit better. We will actually do that during the live demo. So the final steps are recalibration with well data and a sensitivity analysis. For time purposes, I won't go into the sensitivity analysis, but as already mentioned, the uncertainty in the wavelet is very important and can have important effects. So you can investigate what your misestimates in wavelet, what kind of errors would that give. Misestimates in your scaling, what kind of uncertainty would that give. So finally, some words on the limitations of this algorithm. You have inherent geological uncertainty. That is the effect of the internal layering configuration of the reservoir, whether it's front-loaded, back-loaded, randomly, or evenly distributed, in a sense that will have an effect on the average impedance that you will actually measure. And that effect of the layering configuration increases as your apparent thickness of the reservoir increases. It also is strongest for the intermediate net to gross values, because if you have 50% shales and 50% sands, you just have more possibilities to reorganize that stack in different ways. Experts say, as a rule of thumb, you can use this algorithm as long as the gross thickness of your reservoir, your apparent thickness of your reservoir, is smaller than half of the lowest period of the data you have in your seismic colored impedance volume. So if your reservoir is too thick, this method falls down. Other limitations is there should be a bipolar geology. Of course, realistically, that is never exactly the case. But if you have a case where your shales are low impedance, your sands are high impedance, and then you have a fraction of sand shales and silts above that are ill sorted and have even higher impedance, this method won't work. There should be no interference between the reservoir and events above and below. Again, that is unrealistic, but here you can say less interference will give you a better result. The zero crossing peaks of the reservoir on the colored inversion should be clear and accurate. That is a critical step. And further, there should be a single hydrocarbon phase in your reservoir. Those are the most important limitations for this method. So that is the concept and theory behind this workflow. So now I will actually demonstrate how to do it. And for that, we will go to OpendTect. Let me take a quick sip of my coffee. There we are. So this data set will be familiar to most of you guys. It's our standard demonstration data set, F3 in the middle of the North Sea. And the first challenge we had is to find a good interval to do this analysis on. We found one here. We have here a relative clean sand. We have a shaly silty interval above, and we have a somewhat shaly silty interval below, though it's a gradual change rather than an abrupt change there. But we have to work with what we got. And then here, if we go landward, we see that it also has a nice clean sand there embedded in some shales. Some people will recognize this this section. We have some nice channel incisions here with maybe some levees on the side. And actually, I want to give you a real preview on the geology by doing a spectral decomposition. And what we see is this spectral decomposition is in the top of the reservoir interval, and we see lots of spectacular channels, and we like that a lot because they're great on our marketing brochures. However, there will be a nice surprise when applying this analysis in regard with the channels and where we actually want to look for good reservoir. So keep tuned in. So let's have a look actually at the inverted data, the seismic colored impedance. Both the wells and the seismic colored impedance have a color scale where the yellows are the low values and the darks are the high values. And in this case, the low impedances correlate with sands. The lower the impedance, the cleaner the sands. In the seismic color scale, I actually put some whites at the zero. So the white lines here depict the zero crossings, the top and the bottom of the reservoir. And we see that that the horizons there that we derive from our seismic data don't fit the actual reservoir. Here, by the way, we see those incisions again, and what we see if we go to the northeast of those incisions, the reservoir actually disappears. So that is an interesting thing. So the first thing we have to do is actually resnap those horizons on the top and bottom of the reservoir. Effect is here. There it is. So this is about the accuracy that you will need the red horizon and the green horizon to define the bottom and the top and the bottom of your reservoir. And if there's no reservoir, there won't be any horizons. So that is another thing you have to take into account for. The seismic horizons don't have to result in impedance horizons everywhere. So that's now I have my input data, I have my colored impedance, and I have my horizon. So have a quick look at the Seismic Net Pay module. We find that in the OpendTect analysis menu under ARK CLS utilities here, and then the Seismic Net Pay. Quickly running over the menu. Here in File and also some icons, you can actually save and restore sessions. You can also exit, save a parameter report. That's very useful, and do screenshots. And these projects you can actually share among geoscientists, so you can actually send that to one of your colleagues, and he can take off where you left it. There's some visual controllers there. And then in process, we find the process controller. You also find the process controller here in the icons. And then the most important is the help. So let's start the process controller, and we see that we need 3 input data. The average input, which is the average relative impedance in the reservoir interval, the time separation, or basically the isopec, the apparent thickness of the reservoir, and the gross thickness of the reservoir. So I will move back to OpendTect and show real quick how I get those 3 properties in OpendTect for my horizons. So I will start with the most simple one. I take the top reservoir picked on my colored inversion. I right click on it and I go to calculate isopec. I calculate the isopec to my bottom reservoir picked on the seismic colored impedance, and then I calculate that isopec. Done very quickly. Don't forget to save it. Click here, save attribute, give it an appropriate name. I've done this before, so I won't actually save it here. And what we see already here is that that area with the channels actually has the thinnest isopec, so that doesn't bode well for our reservoir thickness. Then the second essential part is the average relative impedance in the reservoir, and you get that also very easily from OpendTect. You go to processing, create grid output, Stratal amplitudes. Stratal amplitudes allows you to do operations between 2 horizons. Quantity to output here would be the seismic colored inversion, which is a stored volume here. I want a window between 2 horizons, and I want to select the top horizon there and the bottom horizon. So now I'm going to do an analysis between the top horizon and the bottom horizon. And on that volume I can output different statistical quantities, and here of course I do the average. So the output would be here average seismic colored impedance reservoir, something like that. Give it a meaningful name, and then you add a result actually on either the top horizon or the bottom horizon here. Remember what you do it. Again, I already did this, so I won't actually apply this, but I will show you the result. Surface data, that is where you find the result. Seismic color inversion, stratal average. Now I've overlain that, and I see that I have my highest average values, which typically coincide with cleanest sand reservoirs, actually away from that channel system. Actually, the channel systems have sometimes even positive values there, so that doesn't bode well for the reservoir quality we find in our channel systems. And then finally, and that is maybe the most involved step, that is an estimating gross thickness from your reservoir horizons. You can do it different ways. You can multiply your isopack with a constant value if you have about constant velocities in your reservoir. You can make velocity models in OpendTect in different ways. You can use the Horizon Cube model maker and interpolate from wells. You can take the velocity model builder. You can import velocity models for migration. In all cases, you can use them. The scenes to create a new depth scene and convert your horizons to depth and create a gross reservoir there. What I did here is I took into account compaction and I took into account lithology variations to true attributes and made a neural network create a velocity volume, and then I used my attribute set to convert locally a pseudosonic volume I created with my neural networks to a local depth range. And I did that for each sample. And then I went back to my processing create grid output, and I just added up all those local depth conversions to arrive at a gross depth for this reservoir. So actually we'll show how that looks in OpendTect. Surface data, gross depth, and we have a small scaling problem here. If I put the upper limit there in my color bar to 50, we see again the variations, and again we see that the area, just like the isopacks, and so that's expected, the area around the channels is actually finished. So we have now all our principal input data, horizons and horizon surface data available. So we go back to the ARK CLS utility, Seismic Net Pay, and we will start working through the process. You started net to gross processing controller, and you have a number of tabs. It almost works like a wizard. You just work through the tabs from left to right. The only thing I have to say, if you change something at the beginning, you have to rework through all the tabs again. So let's define the average amplitude. We stored that on the top reservoir horizon as surface data. Here the stratal average of the colored impedance. The time separation, we stored it as the isopack on the same horizon, and then the gross thickness, gross depth. Oh, my Windows is finding me. And then you apply that by clicking load horizon data, and it will draw this out of OpendTect into the plugin. And what we see now is three plots: an average relative impedance plot for the average impedance in the reservoir unit, a time thickness plot, and then here we see that every point on the horizon we extract the time thickness and the average amplitude. The average amplitude is plotted on the vertical axis, the time thickness on the horizontal axis, and we will use that to scale our tuning curve. So that will be the next step, deriving the tuning curve. And I realize now that I actually forgot one step in OpendTect to show you. So I have to get out of here real quick. Fortunately, I can save this as a project, so I don't have to redo all my work. I can save this as demo 1 here, and then exit. I have to analyze the frequency content of my impedance, and I can do this fairly easy. I go to the layer in OpendTect here, that colored impedance layer, and I select show amplitude spectrum. I get it here from all the way up to Nyquist. This is sampled with 1 millisecond, but that's a little bit too much. I just want to see it between 0 and 100 Hertz. And what I see there is that my lowest useful information in my colored impedance is at least 4 Hertz, and that I really start to have a peak here at 8 Hertz. Then I have the red behavior, I'm biased towards low frequencies, and I have a slope there, a linear slope, as I'm in a logarithmic domain. And then here at this point, my frequency starts to fall off. That is about, you see that here in the lower part, 75 to maybe 80, 85. That is the range where my frequencies really fall off into the noise level. And in practice, I would do that for multiple transacts to the data to see if it's really a constant value. So I can do that here too. I won't go into that detail right now, but it's important to verify that at different places in the data. So let's go to the Seismic Net Pay, open our project again, and go to our process controller. As said, we have to go through the tabs again, but everything will be pre-filled here. And then in the wavelet, we will use that information. For the wavelet was approximately the lower boundaries from 4 to 8, and then the upper boundaries from 75 to 85. Now we calculate the filter response. And we see that we have now a wedge that corresponds to a convolution of your impedance with this bandpass filter, and we have our wedge response and a detuning curve that comes, or the detuning curve will be displayed there. So then we press scale, and we see how the detuning curve goes over the range of the apparent thicknesses here. That scaling, that is important. I want to change my display a little bit here to see a little bit of my more of my range. So let's go to apparent thickness of 100 there. I think these values, these high values here, might be outliers, not related to anything physical. So let's say I want to scale that to 40,000, which assumes that these values here, just around an average amplitude of 40,000 will have, or 400,000, will have a net to gross value of 1. That is basically what you're doing when you're rescaling it. So I say scale again and update map here. So now I have a tuning curve. I go to my velocities. Here I define the ratio of pay velocities to non-pay velocities to get from a net to gross in time to a net to gross in depth. We saw that derivation during the theoretically treatment in the demo. And you can get it easily from cross-plotting a gamma ray versus a sonic in OpendTect, and here we have about a 0.94 ratio. We calculate the time to depth correction, and at this point we can calculate the Seismic Net Pay. You find it here. We have now a net to gross in time. Then we use that velocity ratio to net to gross in depth, and then we will use that gross pay map that we have input to the algorithm to actually arrive at a net pay. And the QC gives us values where our average impedance is actually higher than 1, so that those points are invalid for the algorithm. So you see that these are not included, these points are not included in the calculation. So at this point we can calibrate actually with the well data, and you can load that with hand. You have to load it with the hand for the first time, but once you have done that one time, you can get that information again by storing your project. You have to go to the tabs real quick again to apply everything. So I will do that real quick. 400,000 was my scaling I used there. Scale. This is just pushing the same buttons as we did before. Time to depth correction, calculate net pay. So now I'm at the same point where I was before. But here in my well data, I have pre-filled my well net to pay. That is from a petrophysical analysis, and I did it very roughly, so I assigned very large uncertainty to those net pay values. I left one well out of this analysis because it's in the middle of a gas chimney, so I don't trust the seismic data there too much. We see that one well will be, which has actually very thin pay, is outside the area of analysis because the algorithm rejected it because the reservoir was too thin. So here we can say generate cross plots, and then here we see how those wells compare with the actual prediction. So here we have the net pay derived from the wells that I put into this table, and this is the seismic net pay that is actually present at the well location. Well, it falls within the uncertainty ranges I assigned to it, but I would say that I'm overestimating my net pay a little bit here. So I will go back to my wavelet and to the scaling. I will put it back to 405,000, scale it again, update map. We have to go again through all the tabs, but that's a relative quick process. Generate cross plots, and now I see that my seismic net pay versus well net pay corresponds a lot better. Of course, be careful there. There are a lot of reasons already mentioned that the seismic net pay does not necessarily correlate with the well net pay, but if you see a systematic shift in it, it's worth working a little bit with the scaling factor to get that calibration right. Then there is a tab for uncertainty analysis. We'll browse over that because of time reasons, but you can assign wavelet uncertainty, scaling uncertainties, and investigate the sensitivity to that and get to an estimate of your accuracy of your eventual pay plots. Also, you can here investigate the uncertainty related to well positioning. For a certain well, I can say view matrix, and this is the well position, and I can see actually the relative impedance values around the well, and that is the way I actually derive the vertical uncertainty in this axis. And if I have a larger uncertainty for my well positioning, I can change the grid size around the well. So you can investigate a little bit what would be the effect if my well track is not entirely right on in with my seismic data. So you can get to different uncertainty estimates. And finally, output data. Output data is you output it on the horizon. You can select what you want to output, the net to gross in time, the net to gross in depth here, and the net pay. And then here, you have to select your horizon. You have to select here seismic net to gross in time as new attribute that will be surface data, etc., etc. And then you click on Save Horizon Data, and it will push the results of this workflow from the plugin back into OpendTect surface data elements. So that completes the workflow. So let's have a quick look at the results in OpendTect. I have stored them also previously on the bottom reservoir, just that views a little bit nicer. Add attribute, select attribute, surface data, and let's look at the output net pay in depth. It's displayed at the reservoir in full. And what we see here is that those channels, they are actually partly rejected in the analysis because the thickness of the reservoir is just too thin, or the average impedance within the reservoir is positive instead of negative. But what we see that is the best and the thickest reservoir we find actually in this area. And when we compare that with the spectral decomposition, which is of course only analyzing top of the reservoir, you see that that actually a very boring area. You wouldn't see very much of it. So this is really new analysis. And if we look at the shapes here, we see some turbidite channel coming in, a big fan, and then on the other side of the fan we see kind of a meandering channel coming out of the fan where the basin floor is relatively flat. So thinking a little bit about this and putting this in a geological context, what I think has happened is that one or two turbidite flows have deposited a big lobe here during a falling stage event, and then in the subsequent low stand where we still have the high energy, but we have high energy turbidites, but we have low density turbidites, underloaded high energy features that actually in size, those low energy turbidites or low density turbidites that are not that interesting for exploration actually left all those incisions, but the real interesting reservoir is found elsewhere and is actually highlighted by the algorithm. So I learned really something new from this algorithm about our data sets, which was really exciting and very relevant to developing and exploration. So let's wrap this up. Let's go back to that PowerPoint from current slide. We don't want to do it all over again. Let's recap. This plugin gives you essential data for both economic appraisal of the reservoir and the development of the reservoir. The principal input is the colored impedance or relative impedance volume, and also your horizon tracking. The horizons are of course important, but you do that on the colored impedance. So that is the volume, the principal data that your whole algorithm revolves around. It's an easy workflow. What you do need to know, and what's fairly critical, is the frequency range in your relative impedance volume, your best scaling factor that you derive partly from your scatter plot and partly from your well calibration. It's actually such that if you have your frequency range slightly wrong, that with the well calibration and the scaling you can partly compensate for that, which makes the algorithm more robust. And finally, you need a velocity ratio, a good hold in your velocity ratio between your pay sands and your shields in your reservoir to get a proper conversion from net to gross in time to net to gross in depth, seismic net to gross, that is. The algorithm is robust in the sense that a good scientist, a good geoscientist with a good colored impedance input data generally will have good output results. The principal outputs are a net to gross map, both in seismic net to gross, I have to say, divided by apparent thickness, both in time and in depth. A net sand thickness and depth that you can correlate with your wells, and uncertainty estimates. But we didn't talk about the uncertainties, but if you have questions about that in the subsequent answering questions session, please shoot. And then finally, I hope that this gave you some interest in the plugin. Unfortunately, I have to disappoint you. The plugin is not right now available. It will be released at the EAG begin June in Copenhagen in OpendTect 4.4. If you're interested and you want to evaluate it, there are evaluation licenses available, and you can request one via info@dgbs.com, and we just put you on the list and send you a license as soon as the software is available. Or during the EG conference, you can visit ARK CLS in booth 802 or DGB in 840 for a demo for more information and to get a demo license. So with that summary, I'm concluding my demo, my presentation. This will be followed by a question and answer session moderated by Venice. So here, Venice, back to you.
Okay, thank you very much, Friso. I am sure this was very useful for everyone. So please now, if you have any questions, just feel free to raise your hand and I will unmute you, or you can write your question in a question pane. This is your time now to ask your question. Okay, Liz? You can say your question. Liz, I unmuted you. You can feel free to ask your question. Okay, you write it. Okay. Okay, I assign the question to Arno, and you will have the answer very soon.
Yes, the question is if we have any experience with very steeply dipping reflectors. I guess personally, we would not have a very specific experience with this, but in general, it all comes when you have very steep reflectors to the quality of your imaging. I guess one of the most important factors for this kind of interpretation technique to work is that you have to have true amplitude processing on your seismic data. And that, of course, becomes more challenging if you have steeply dipping reflectors. But apart from this, the dip is not specifically involved in this workflow.
Okay, we have another question here from Philip. Yeah, Philip, go ahead. If you would like to, yeah.
My question is, on the slide, it's slide 27 when it says other limitations, and it talks about a bipolar geology. Yeah, I wondered if the speaker could just say a little bit more, give me an example of that. I'm just trying to understand exactly what that means.
Please, this is Friso, I can answer that.
Yeah, sure, go ahead.
Question. The question is, bipolar geology, what does it mean? The whole derivation of the algorithm is based on models that have a shale with one impedance and a sand with another impedance. And they can be in layers. The layers can be very thick or very thin, and they can be in all kind of random orders, but it's either a shale with impedance A or a sand with impedance B. Of course, that is a very strict or very unrealistic model in a certain sense. And in practice, what I understand from our own work here and from the publications, there's some leeway there. I mean, it doesn't have to be a sand with just a very narrow range of impedance and a shale with a narrow range of impedances. You will in practice have grades. You have clean sands, you will have sands with a little bit silt in it, etc. It will be robust to that. What it shouldn't have is, say, a shale that is very low impedance, a sand that is in the middle impedance range, and then some dirty sand with sand mixed with shale in the high impedance range, such that your good reservoir is wedged between two impedance ranges which are bad reservoir, or a completely like fluid geology. There should be some binary behavior, like I have a turbidite and then I have more pelagic shaly deposits and I have a turbidite again. So that is what you have to think about with a bipolar geology. Does that answer your question?
It does. Thank you.
Yeah.
Okay, great. Any other questions? Okay, Ahmed, go ahead.
I ask if this method can applied in high structure area as Gulf of Suez.
Okay, Ahmed, can you repeat your question again?
Okay, this method can apply in high structure area as Gulf of Suez.
Venice,
Yes.
maybe one of the people who have a little bit more experience with the algorithm. I don't know if Adrian would be the appropriate person to answer this.
Okay, Adrian?
Well, okay, then I will take the question. The question was, can we apply this algorithm with in areas with a lot of structure? There are two things to take into account there. First of all, there is no principal point why you couldn't. However, there are two things that are the gentleman noticed the Gulf of Suez as an example. There are two things you have to take into account. If you have a lot of structural relief, there might be more than one calibration curve applicable because you will have different due to compaction and diagenesis due to different burial depths. You might have different relationships between your sands and the shales depending on where you are in your burial curve. The second is in areas like the Gulf of Suez and other rift areas, definitely the rift phase, you will have a higher variable input into your reservoir, so or into your formation. So you're literally your reservoir properties might be less constant than you might have in a deep water setting. So those are not things that would inhibit the application of the algorithm, but are points that you have to take into account when applying the algorithm, that you have to calibrate maybe for a Graham block different than for a Horst block, and that you have to watch out with your sediment input points that they might be more variable than in a deep water setting. Does that answer your question, Ahmed?
Okay, thanks, Bob.
Okay, great. Okay.
I would like to, this Arno speaking, I would like to pose another question. Maybe Adrian could answer this. The question is if the SMP plugin would come in bundled with the colored inversion plugin.
Hello, can you hear me?
Yes, we can hear you.
Yes, we would certainly bundle it with SCI because we think it ties together. We're already bundling it on various platforms, so I see no reason why we wouldn't bundle it as a plugin to OpenTect.
Okay. Philip, do you have any other question? I can see your hand. I guess he was just saying thank you. So, okay. All right. I can see here Ali. Ali, okay, go ahead with your question.
Yes, hello.
Hello.
I'm Mohsen. Hello, I'm the co-operator of Ali, and I attended instead of him because he was busy now. I have a question. What's the effect of utilizing high-resolution geostatistical inverted acoustic impedances instead of relative acoustic impedance in the algorithm? Does it improve the results?
I guess there's Some of the panelists needs to just mute themselves that we can hear clearly.
Yes, I would say that there are advantages and disadvantages in both broadband inversions, so a standard acoustic impedance inversion or broadband elastic impedance inversion. But this technique is more robust, has its advantage in the fact that it does not use any input low frequency model, because the main input is colored inverted impedance. And because of this, it will not suffer from any problem related to the low frequency model that you have. And you can estimate from this technique your net pay maps without the need to input a low frequency model, and that is specifically because the amplitudes are detuned in using the models you have seen into net pay values.
Thank you.
Okay. Okay, I don't see any more questions. Is there anybody has any more questions? Okay, great. I want to thank everyone participated today, and I want to thank you, Friso, again for the presentation and for all our panelists and that they were answering the questions. I'd like to tell you that you are going to have a link for all the recording session that we have today, and you will receive it by Friday. And also for those who are new to our webinars, I just would like to tell you that we have one every month, so you will receive a link with the webinar that you can participate with us next month, and we will be talking about Horizon Cube and well correlation panel, and this will be around mid-June, and you will have the link with the date and with everything. If you have any question after listening to the presentation again, please feel free to just contact us via email at webinar@dgbes.com, and we will be glad to answer your questions. Okay, thank you, and hope to see you next month. Thanks, everyone.